So in today's lesson, I want to introduce you to the ideal gas law. But in terms of solving these kinds of problems, there's not much new here. It's the same process as we introduced to you when we first looked at how to solve problems with just Boyle's law, where you interpret the problem, find your knowns and your unknown, make a list, choose the correct equation, plug it in, and chug away. The kind of math we're going to use is the math you've been using for years and some of the math that we've used in previous units. All right, let's look at these problems. The first one here says that conditions of 785 torr pressure and 15 degrees C temperature, a gas occupies a volume of 45.5 milliliters. What will be the volume of the same gas at 745.0 torr and 30 degrees C? So the first thing you want to do is make a list of the things you know and the unknown you're trying to find. So let's see, 785 torr, it says it's pressure, so we're going to list that as P. And then we got 15 degrees C temperature. Well, it says it's temperature, kind of helps you out there. We need to change that to Kelvin because you can't do gas law problems in degrees C. So I'm going to go over here and take this 15.0 degrees C and add 273.15 to it. I've got an empty slot over this 5 here on the end. And so we get 288.15. So what you guys got? Okay. And we want to round that off to get rid of the 5 on the end. So 288.2. That's really the temperature we want to use, 288.2 K. So you just follow this same process, finding the knowns and finding your unknown and making a list. Now if you look at your test references, you'll see that the combined gas law is listed there for you. Have y'all looked at that? Okay, so on your test references you've got P1, V1 over T1 equals P2, V2 over T2. Okay, so we just plug stuff in there. So we've got P1 is 785 torr. V1 is 45.5 milliliters. T1 is 288.2. P2, 745.0 torr. T2, 303.2 K. And V2 is 0.15. And now you need to get this unknown by itself. Okay, I call it isolate. Okay, you want to get it by itself. That's when you isolate it. And the easy thing to do is you want to multiply by this and divide by that. If you're going to multiply by this, we're going to put it on the top. And we're going to divide by this, 745.0 torr. Okay? And that allows us to cancel this, and because I've got that on the bottom, and cancel this because I've got this on the top and bottom. But whatever I do to this side of the equation, you can't forget you got to do it to the other side of the equation as well. So this same fraction needs to be put over here. And now you just cancel your units, just like we did in those when we're doing stoichiometry. You're just going to cancel units. Got torr canceled here and Kelvin canceled here, and put it in the calculator the same way we did it in stoichiometry. Now this is the fast way that works with every calculator. You don't have to have a special calculator to do this. Multiply everything across the top and hit equals 303.2 times 785.0 and times 45.5. And this is the same system I taught you when we're doing stoichiometry. Press enter or equals, then divide by this number, this first number here, divided by 745.0, and hit enter or equals, and then divide again by 288.2, the second number on the bottom, and hit enter or equals, and then you get an answer. And that'll be this will be the answer once we round it off. We've got units of milliliters left, and that's going to equal V2, because that's what we have left over on this side. Okay? And then we underline the insignificant digits. Looking at all the measured numbers I have in here, this one right here has the least digits, 3 digits. So we want our final answer to have that same number of digits. 50.4 milliliters equals V2. Does that make sense? The only thing really new here is listing your knowns and unknowns and finding the right equation. After that, it's the same algebra and stuff you already know. So 600 milliliters of air. Let's list that first. That's a volume. 600.0 milliliters. 20 degrees C, that's a temperature. And it says what's the volume? This is a new volume. This must be volume 1 up here. This is volume 2 at a temperature of 60 degrees. That must be temperature 2. 60.0 degrees C. Obviously, we're going to solve that with Charles' law, but you got to know when you see temperature in degrees C, little bells and whistles should be going off in your brain and saying, got to convert to Kelvin, got to convert to Kelvin, got to convert to Kelvin, right? And instead of these two temperatures, we're going to say that that is 293.2. And in your test references, Charles' law is not listed, but the combined gas law is. And I'll show you in a minute, even if you don't have it written down, if you could use the combined gas law and realize, you know what, pressure's not changing, I don't need it. Does that make sense? And just drop it off. But we'll go with Charles' law here. Going to plug in what we know. We know volume 1 is 600 milliliters. Plug in what we know for temperature, 293.2. V2 we don't know. T2 is 333.2 K. And then you're going to use the math skills, algebra skills you already know. Alright, we're going to isolate this V2 by itself. I know you guys want to do cross multiply and stuff, but I've seen it trip up a lot of students because they don't really know where to use it appropriately. So I'd rather you not use it at all. This cancels completely. The K's cancel here. We have milliliters and volume. We know that milliliters measures volume. We're ready to plug it in the calculator. Looking at the measured and calculated numbers, I can see I need 4 digits in the final answer. Round it off. 681.9 milliliters. Does that make sense? I mean, once you start doing this stuff, it's all the same. It's always just find your list of knowns and unknowns and plug stuff in.
Glade Fresh.
Plug it in, plug it in.
Got a gas that occupies 12.3 liters at a pressure of 440.0 millimeters of mercury. 12.3 liters is a volume. Pressure is 40.0 millimeters of mercury. And we want to know what the new volume is. So we don't know what this new volume is. We're going to try to find it. So this would be V2 is what we're trying to find. That makes that V1 and P1. And I said we're going to increase the pressure. So this new pressure goes along with this new volume we're trying to find of 60.0 millimeters of mercury. Don't have to convert any temperatures here. Just got to put it in the right equation. Well, let me show you this real quick, because P1 V1 over T1 is what's in your test references. P2, V2 over T2. Okay, if you don't have your test references out, it wouldn't hurt for you to look at it. Okay, since temperature is not changing here, we don't need temperature. Does that make sense? If it's going to stay the same, whatever it is not going to change anything in the equation. We're not going through a whole bunch of stuff about how the math works. Just take my word for it. We can drop that off. And there's Boyle's law. Does that make sense to you? That make it simple? Okay, so really what we're working with then is P1V1 equals P2V2. So if temperature doesn't change, we only need what's on the top. If pressure doesn't change, we only need, I can't turn my hand around far enough to get it there, but you only need that part of it. Does that make sense? Okay. All right, so let's see. We got 12.3 liters for, well, let's start with the pressure, 40.0 millimeters of mercury. Times V1 is 12.3 liters. And P2 is 60.0 millimeters of mercury. And then V2, we don't know. And we want to isolate. I get 8.2 liters equals V2. And that's what the calculator says. I'm looking at these numbers up here, and I see they all have 3 significant digits. So I really need this answer to have 3 significant digits. And so we just put a 0 here. So if you have your test references, well, whether you have your test references are now out or not, you need to get them out so I can show you this. Make sure you're seeing this. These are the references you can use in an honors chemistry class, because these are the same references you use on an AP chemistry test. So this is a prerequisite class for AP chemistry. I want you to use these references, okay? So you kind of get used to them. Here's the combined gas law. See if you can find that on your list there, and make sure you know where it is. Okay, it's right there. Charles' law is not listed in the references, but it's pretty easy to devise it. When you're reading the problem, if there's no pressure change, we can delete the pressure from the equation, and we get Charles' law. So if you look down here in the lower right, that's Charles' law, and it's the same equation as that law that you have listed on your references, but without the pressure. Does that make sense to you? In the lower right, that's essentially Charles' law, and the equation above it is what you have on the references. And all I did was take out the pressure. So if you've got a question that's asking you, got an initial volume, an initial temperature, got a change in temperature, what's the volume? Well, you're not changing any pressure. So you just drop it off. Does that make sense? Okay? All right. I mean, if we did the math, we could just divide it out anyway, so it wouldn't matter. All right? And Boyle's law is kind of the same way. If you have a question for which there is no change in temperature, but there's a change in pressure and volume, then you just drop the temperature off. So you can see the equation here. Boyle's law is not listed in the references. You can derive it. The equation there in the upper right, that's what's on your references. That's the combined gas law. And if we have a question that deals with Boyle's law, you just drop the temperature off and you got that equation. Yes? That makes sense? Now you still have to know what Boyle's law is and what Charles' law are. Okay? But as far as solving problems, you can look it up. Okay, and use what you need. Everything you need to solve these problems is on that set of references. That's kind of nice. Okay? So here's something new we're going to deal with today, and this is called the ideal gas law. It's sometimes also called the perfect gas law. Looks like I forgot to close my parentheses there. Okay? So if you look at that, it's right above where the combined gas law is. Okay, it's right at the top of that column. The R in the ideal gas law is the ideal gas constant. And all the other symbols, well, even R is defined for you in the references. Okay, and some of these you already know. We've already worked with pressure and volume and temperature. And I'm telling you now that the R in the ideal gas law is the ideal gas constant. I'm going to tell you now that N, the lowercase letter N, just a symbol we use for moles. On this part of your references, if you look, you can find all those are defined for you. Pressure, volume, temperature. And in the bottom part of the page, well, there's your gas constants down there. So let's just isolate those a little bit. Here's the list of the the variables, okay, the symbols. Okay, P is pressure, V is volume, T is temperature, and there's N equals moles. Capital D is what, in these references, used to indicate density. Mass is listed here. Velocity is this sort of Greek letter V. Okay? And then, if you look at the bottom of that same section there, you'll see the gas constants we're talking about. Okay, R. Now, there's 4 different values for R listed down there. Actually, the values, 2 of those are the same, but we're only going to use 2 out of these 4 anyway, because the ones we need have pressure units. Okay, and what you're going to do in a problem is you're going to find the value of R that matches the pressure units you're using. That's all you got to do. Okay, so if your question has pressure in atmospheres, we want to use the second value of R. See what I'm talking about? Because that's where atmosphere is listed. If you want to use pressure in torr, it's the third one. And the first 2 we don't even use because those don't even have any pressure units. At least in gas laws, we're only going to use the middle 2 because the first one and the fourth one there don't have any pressure units, okay, in this unit of instruction. So, only using these 2 right here. Only 2 of these values have pressure units in them, so we're only going to use those in this unit. So, the pressure units we have in here are atmospheres and torr. You just got to match those to the problem. What else in the problem is listed in atmospheres or torr? That's what you use. That's how you choose which one of these values of R to use. You got that? Let me show you something else that's on your test references, and that is that on your test references it tells you that 1 atmosphere is equal to 760 millimeters of mercury, which is also equal to 760 torr. So while there's no value for R when the pressure is in millimeters of mercury equals torr, that's shown in the references, so we can just plug it in. Okay? Plug that millimeters of mercury in for torr, and we get the same value, just plugged in millimeters of mercury for torr. So really you've got 3 there, even though 1 you kind of have to derive. One more thing that's important is that when you're doing the math, in order to cancel units and make sure you get the right answer, that you set up your problem correctly, is you need to be able to look at the way they listed in the test references and mentally convert that into a fraction. And that's what I've done for you here. 62.4 liters times millimeters of mercury times the inverse of moles times the inverse of Kelvin is the same thing as a fraction, where I put moles on the bottom and Kelvin on the bottom of a fraction. Okay? It's something to know because a lot of references are listed that way, not just in your AP test references. Okay? And so if we're using the value for R that has torr in it, you just got to know moles and Kelvin go on the bottom of a fraction. See what I'm talking about? And then if we're using the one that has atmospheres, moles and Kelvin go on the bottom. Hey, moles and Kelvin always go on the bottom. Look at that. Does that make sense? Okay, so every unit of R, every value of R we're going to be using will have liters on the top, moles on the bottom, Kelvin on the bottom, and the only thing you have to look out for is the pressure unit. Okay? Just got to choose. Find the right one. Just a scavenger hunt. We've got to find the right value of R. Okay? And the question will tell you, you got units in the atmospheres or units in torr, you just got to find the right R. All right, now one more thing to remind you about or tell you about and show you. It's in the references. Okay? When we talk about STP, standard temperature and pressure, we list standard temperature as 0 degrees C because it's easy to remember. You already know that 0 degrees C is 273.15 K, right? So, it just stands to reason then that standard temperature is also 273.15 K. If you have standard temperature and pressure, you could just write it as 273.15 K and forget the conversion because you know that's what it is, yes? That makes sense? So it can save you some time if you remember that 0 degrees C is 273.15 K. If you're given a problem where you have to have STP, just plug in 273.15 because our gas laws have to be solved in Kelvin. That might help you out. Might speed it along. If you don't remember it, it's okay. It's in the references. You can find it. Okay? Standard pressure is 1 atmosphere. We always list standard pressure as 1 atmosphere. But the references show you that 1 atmosphere is 760 millimeters of mercury, which is also equal to 760 torr, which we went over a while ago. So you know then that standard pressure is, in addition to being 1 atmosphere, is also 760 torr and 760 millimeters of mercury. Maybe this will help you. Problem-solving system. ILLIS. If you want to remember this, if this acronym will help you, great, do it. It's just a way to try to help your mind, help you remember how to set up these problems so you just about always get the right answer. If you just follow all the stuff you already know, okay, all the math stuff you've already learned, just do this, okay? You got to interpret the problem so you can make a list of knowns and the unknown, okay? Interpret the problem, make a list of knowns and unknowns. So then you're going to list then the equation based on that interpretation. You got to choose the right equation. The reason I want you to write them down in a list, that is to say, the reason I want you to write down the list of knowns and the unknown is because, you know, there's kind of a lot to keep up with when you're first approaching these problems and you're kind of newbies at this. If you write it down, it's not so hard to keep up with because you've got to look at it. Okay, finding the equation is easy if you make a list. So you're going to interpret the problem, make a list of the known and unknown values. You're going to list the equation. You're going to isolate the unknown. You're going to do that by plugging in the values you know. And you're going to solve. You cancel units and solve the problem. So the problem says we have 2.34 grams of carbon dioxide. That's what I listed here next to the M for mass, because that's the symbol that's on your test references for mass. It says we want to find the volume, so I'm going to put a question mark next to that. We have STP. Well, standard temperature, we just talked about this, is what in Kelvin? Because we want to have it in Kelvin. 273.15. Okay, so we didn't have to do any math to calculate that. I didn't have to convert it. And standard pressure, we could use torr, 760 torr. We could use millimeters of mercury, 760 torr. But it's a whole lot easier to use 1 atmosphere, right? Because, I mean, well, make it easy on yourself. There's nothing in here that says we have to use torr or have to use millimeters of mercury. So you try to find the easy way, right?
So that would be easy for every problem?
List your knowns and unknowns. Now, the only tricky thing here is we don't have an equation that quite fits this. But in the last unit, we did the same, this one little conversion over and over and over again that's going to give you the one thing we don't have. If we have mass and we know the species, we can find moles. Remember molar mass? Right? All right, let's calculate the molar mass of CO2. Carbon, oxygen. Carbon is 12.01. Oxygen is 16. We've used that so much you've got it memorized, haven't you? .01. Okay. Now that's grams CO2 equals 1 mole of CO2. All right? That's the way I taught you to do it. Make sense? Yep? Okay. So now we can convert this into moles, can't we? You know how to do that. This is a yawner here because you know how to do this. Isn't it? Yeah? Yeah. All that? Remember that? I mean, how many times did we do this in the last unit? Over and over and over again, didn't we? Okay. Cancel out grams, cancel out CO2. Okay. And do the math. 2.34 divided by 44.01, 0.0531,697, 34151, 34151. Almost run off the page here.
What if I didn't know that fast?
That's okay. You write down the numbers that your calculator gives you. Your calculator doesn't have to give you the same number of digits mine does. Okay? Whatever your calculator gives you. Alright? And that's grams of CO2. I'm sorry, that's moles of CO2. And then we need to round it off. 3 digits. Leading zeros are not significant. 1, 2, 3. 0.0532 moles. Okay? So now I can put N over here in the list. 0.0532 moles. Got that? Let's see. Just kind of ignore this top one here a minute. VTPN. What equation do you have on your test references that has those things in it? Ideal gas law. And R is listed on your references, isn't it? Make sense? So we've got PV equals nRT. R we can look up, and we just plug it in. So the question that I have for you is, do you want to solve for V before we plug anything in, or do you want to plug things in and then solve for V? And would you want to isolate in the beginning, or isolate as our sort of a step 2? I'm going to do the isolation first, because getting V by itself is pretty easy here, isn't it? If I divide both sides by P, then P cancels on this side here, and I get V by itself. So what I've done is just change the equation around so that I have V equals nRT over P. Does that make sense? We know we're looking for V, and we can either plug in everything we know first and then isolate V, or we can isolate V to start with. I think it's easier if you isolate V to start with. And you can do that with any other gas laws too. If you prefer to isolate your unknown before you actually plug in any values, that's okay. I find that easier. I haven't taught it that way up to now, but you can see how it's easier here, right? Okay? So let's see. N is 0.0532 moles. R, let's see, we need to find the right R that matches this pressure unit. There's only 2 to choose from. Okay? Which one of the R's has atmospheres in it? So look on your test references and figure out which one of these R's has atmospheres in it. 821 liters times atmospheres over Kelvin times moles. Now it's really important that you're careful that you really listen carefully here. I have students that from time to time, well, almost every time we get to this unit, somebody's going to want to plug in numerical values for these. These are not variables you can plug things into. These are units of measurement, okay? You can't plug things into R, okay? Those are the units of measurement that go along with this number. Everybody with me? Please try to remember that. Don't make that mistake. All right, then we got to have T in Kelvin, because all of our temperatures and gas laws have to be in Kelvin. So 273.15 K. And then all of that has to go on top of P. And that's 1 atmosphere. Okay? All right. Very good. I'm glad you said that. Okay? she just described something that I was always taught. Of course, I'm a lot older than you guys. I don't know if they still teach you this way or not in math classes. But when you have a mixed fraction like this, a complex fraction it's called, multiply the reciprocal, okay? I always remember it as invert and multiply, okay? Now, there's a famous poem called The Charge of the Light Brigade. And the famous line from The Charge of the Light Brigade,
theirs not to make reply, theirs not to reason why, theirs but to do and die.
so we always remembered invert and multiply using that by plugging it into that line in that famous poem. And we remembered it this way. Ours is not to reason why, only to invert and multiply. Okay, so that didn't help you. Anyway, boo, he says. Oh man, okay, broke my heart. All right, so here, put all these over 1. All these that aren't already in a fraction, put them over 1. Okay? And then we're going to rewrite everything on the top just exactly the way the top appears. And then we invert the bottom and multiply. That's what they invert, multiply, or multiply by the reciprocal means. Okay? So we're going to take and flip this one. 1 over 1 atmosphere. Okay? All right. Now we just got to do the same thing you've learned to do before. Later. And even though this problem's kind of long, the only thing new is interpreting the problem to find your list of knowns and unknowns, and then choosing the right equation.